Free space optical communications isn't just about shooting laser through the air. The heart of its performance lies range-link equation. Let's break down this essential formula and see how it shapes FSO system design. So let's consider here a simple experiment and see of what elements our system is composed. So any free space optical communication systems at the minimum will be comprised of the following elements. So we'd have optical source, would have some sort of transmitter aperture with diameter dt. We also would have receiver end with receive aperture diameter dr. Would have a detector with some sort of efficiencies. We know that when the laser would emit a signal when the laser would emit signal, the signal would diverge with some divergence angle that we call theta divergence. And we know that finally we detect the signal at the receiver's end. So the idea is that fundamentally the range link equation describes the received power received at the detector as a function of several key parameters. So once again, the power of the laser beam leaving the transmitter. Higher power means stronger signal, but also increased power consumptions. So also we have optics efficiency. The efficiency of the transmitting and receiving optics losses here can significantly reduce the signal. Transmitter gain. How well the transmitter focuses the beam. A tighter beam means more power reaches the receiver. Pointing loss. Misalignment between transmitter and receiver can lead to power loss. This depends on beam divergence and pointing accuracy. Space loss. The natural spreading of the beam as it travels through space. This loss increases with distance. Atmospheric loss. Absorption, scattering, and turbulence. In the atmosphere can weaken the beam, especially over long distances. Afterwards, we have receiver gain. How well the receiver collects the incoming light. A larger apertures increase gain. And also receiver area, the physical area of the detector. A larger area captures more of the signal. By manipulating these factors, we can optimize the performance of an FSO system. For example, we can increase transmitter power, which leads to stronger signals, but at the cost of higher power consumption. We can also increase transmitter receiver aperture size, improves gain, but can make the system bulkier and more expensive. We can also minimize pointing errors and atmospheric losses, which requires sophisticated technology like adaptive optics, which cannot always be the case, for example, for spaceborne applications. Well, the range link equations is not just theoretical, it's a practical tool engineers use to design and optimize FSO links, ensuring reliable communications over the intended range. Understanding this equation is the key to unlocking the full potential of free space optical communications.